And second, let me share the screen. And do you see it, guys? Did I share it one more time? Okay, so here we are. So this is from your textbook. What is life, right? So this is chapter 2. And this is about chemistry of life. So as I said, the very, very basic. And I told you, whenever I talk about world around us, right? Everything is made of matter, both living and non-living. So matter, including us, if you start breaking down to the smallest part, you get to chemical elements. So chemical elements, by definition, is the smallest, the tiniest part of matter that you can further break it down into another substance, right? So that's it. This is like the end of the road. So chemical elements, again, make up everything around us, including us. Chemical elements, in their turn, are made of atoms, okay? So if matter is made of elements, elements are made of atoms. And I want, before we're gonna go into atomic structure, there is something I want to show you right now. And this is, since we talk about chemicals or in atoms, that you probably saw at school at least once, right? Steven, have you ever seen this?
Yes.
Steven, what
Oh,
about?
yes, I do. That's the periodic table.
Yes, this is the periodic table of elements, okay? Periodic table of elements was actually organized by a Russian scientist. His name was Dmitry Mendeleev, and he claimed that he saw it in his dream. Periodic table of elements is a beautiful thing because it actually gives you information about all elements so far known, not only in this world, but also in space, for example. And once you look at this table, you actually see things that are familiar to you, I promise. You're gonna see a lot of familiar things that you probably didn't just think about it. So, as I said, elements make up matter, right? Elements made of atoms in their turn. And if you look at each element, first of all, they are organized by atomic weight. Even though atoms are so tiny, you can't see them without, even like with the powerful microscopes, you can't see the atoms, right? Even being so tiny, they still have weight, the atomic weight. And Mendeleev organized them from the lowest atomic weight to the heaviest. At the time when he worked on periodic table, some elements were not even known at his time, right? A lot of elements were added into the table years later, but he said that the first one with the lowest atomic weight is hydrogen. Hydrogen is believed to be the first element in the universe. I'm sure you heard that the theory that universe was formed by Big Bang, right? Explosion, Big Bang, right? And it's believed that the first element that appeared after Big Bang was hydrogen. And the rest of chemical elements were actually built upon hydrogen. So hydrogen is the gas, okay? And hydrogen is the most abundant chemical element in our world as well. Why it's so abundant? Because if you take one, like if you take two hydrogens, 2H, right? And combine with oxygen, you get H2O, which is what?
Hydrogen, oxygen.
H2O.
Is water?
Water, exactly, right? And water is the most common substance, right? And water actually makes up more than half of your own body. So here's the oxygen O, right? So you continue from hydrogen, you get here, the next element is helium. And I'm sure you heard about helium, right? Something interesting about this element, it was first found on the sun. Then it was also discovered on Earth as well. Helium is a gas, and people use helium for what?
To fill up balloons.
Exactly, absolutely. What else? If you inhale helium, how are you gonna sound?
Got like a squeaky voice.
Yes, like a chipmunk voice, right? That's the helium. Then this column, these are metals, right? Starting from lithium and sodium, and you continue with the metals here. And these are non-metals, and these are gases. They're also called noble gases. All these gases are quite interesting because they don't really react with other elements. They don't form molecules or compounds. They're pretty much on their own. So here, we're gonna talk a lot about carbon. This is another gas. Carbon is not a gas, but this is a gas, nitrogen. This is the most common gas in air that we breathe. We have more nitrogen in air than, for example, oxygen. This is a fluorine. You all know fluorine. It's added to what?
Fluorine.
Fluorine is added to your toothpaste, right? To keep teeth healthy.
For drinking water.
Yeah, and water. Neon, you all know neon, right? Neon is used for lights, right? Neon lights. Here is the latest metal called aluminum, okay? It's a metal, but it has a very light weight. Because it's so light, it's used to make what?
Is it in airplanes?
Exactly, absolutely. Aluminum is used to make airplanes and a bunch of other things, for example, aluminum foil, right? Silicon, you know it's a part of sand. Like silicon salts actually make up sand, but also silicon is used to make what? No, come on. Silicon is used to make implants, right? What kind of implants?
Oh, breast
Like
implant?
construction.
Breast implants.
Breast implants.
Absolutely, yes, this is the silicon. Phosphorus, right? The one that glows in the dark. Sulfur, that smells bad. Chlorine, which is the part of the table salt. You take sodium and chlorine, you get table salt, right? Another very important element, calcium, is crucial for your teeth and for your bones. Another one, iron. You all know iron, but iron is a very important element for your red blood cells. So your red blood cells can carry oxygen to your tissues, okay? What's a good source of iron in your diet? Tell me. Because without iron, people develop what? If you don't have enough
Energy, I think.
you have no energy, anemia, right? The most common anemia is iron deficiency, right? So what's a good source of iron? What should you eat for iron?
Isn't it usually in meat?
Meat, absolutely, yep.
Like
What else?
beans.
Beans. But let me tell you something interesting about iron. Like, I mean, it's not like issue to get food that is rich in iron. The issue to get food that your body will take iron from. For example, you have iron in apples, right? You also have iron in meat. But your body will take iron from meat much better than from apples. Let's say to get the same amount of iron from one steak like this, okay, you have to eat like a pound of apples. That's the difference. That's why I said it's said better to eat meat for iron than anything else. So iron, then you have, for example, copper. There's a bunch of things are made of copper, I'm pretty sure you know. And I want to show you a few things as well. Look, silver, silver, argentum. By the way, which country is called after silver?
Gold.
No, which country is called after
Oh.
silver?
Oh shit.
Argentum.
Not sure.
No, come on.
Argentina.
Argentina, exactly, is called after silver. Right under silver is another precious metal is gold, right? Aurum. And I believe so many places are named after gold. Next to gold is platinum. You know, platinum is even more expensive than gold. You know that. And right next to it, another very expensive metal, but it's a very toxic metal, is mercury. Mercury is the only liquid metal known, right? And actually handling mercury, handling is quite, as I said, quite dangerous. So what is mercury used for? People
Light
use
bulbs.
No, God forbid. Not light bulbs.
No?
Mm-mm.
Oh, that's weird. I work in a school and I was told like if one of the fluorescent lights break, that
Mhm.
it's like it has like mercury in it, something like that. It was
Maybe
supposed to be toxic for.
maybe fluorescent lamps, but regular
Oh, okay,
lamps,
okay.
you have another one, you have wolframium. But
Is mercury thermometers?
thermometers,
Thermometers,
exactly.
yeah.
Yes, old thermometers. Barometers to measure pressure, that's the same mercury. Now, the heaviest metal is lead. It's also very toxic, right? Lead was used a lot in old days. People use lead to make pipes, to make containers, to make paint, right? Which is, you can do it in these days, right? Because it's known that it's not a good thing. They also used lead to make gasoline, right? Now, lead is the heaviest metal. So people also use lead to make what? Since it's the heaviest.
Buildings? No?
Bullets. People use
Oh,
lead to make
bullets.
bullets. Yeah. And what else I can show you here? Interesting. By the way, this is radon. You all heard this is radioactive gas. And if it leaks, it's actually a medical emergency, right? You have, these are radioactive elements. I don't know if you heard about plutonium, I'm sure. You heard about uranium, right? And this is uranium. And what else is interesting here? I mean, again, it's quite interesting table, to my opinion. You can learn a lot of things from this. And yeah, so from all chemical elements that you actually see here, only 92 are found in nature. The rest were discovered in the lab, and some of them maybe existed for a very short period of time. From all 92 elements that you see here, 4 are basically make up a bulk of living organisms. And the bulk of living organisms is made of hydrogen, carbon, nitrogen, and oxygen. So let's go back to PowerPoint. Here, actually, you can see gold, right? Carbon. Carbon, what you see, it's a coal, and carbon also makes up diamonds, pure carbon. This is copper, for example. And let's talk about the atomic structure, okay? So as I said, everything is made of chemical elements, and chemical elements in their turn are made of atoms. This is their basic structure and the model of atom that is used until these days. And the model is said that atoms are made of particles on their own. And the particles form 2 parts. The central part is called the nucleus, the very center of the atom. And in the nucleus are 2 types of particles: protons that have positive charge and neutrons have no charge. Around the nucleus, you're gonna find particles called electrons. Electrons have negative charge, and electrons move around the nucleus, and they move so fast that you don't even see them like orbiting. One electron can form like a cloud around the nucleus, okay? So protons and neutrons in their nucleus, electrons move around the nucleus. Now in the atom, number of protons, and electrons, the same, which means that the net charge on the atom is what? If you have the same number of protons and electrons, so what will be the total charge on the atom, guys?
Isn't it 0?
Exactly, Sarah. Awesome. 0. Absolutely. Okay. So if you look at their periodic table, you can learn a lot of things about each element. So each element has a symbol. This is oxygen, right? Symbol, name, atomic mass, and one more time they arrange in table from the lowest to highest. It has a number, right? So what's really interesting, significant about the number, once you look at the number of the element, it actually tells you number of protons and electrons, okay? So for example, if I go to the periodic table, so I look at, for example, lithium. Lithium is number 3, right? This is the atomic weight of lithium. But number 3 means lithium has 3 protons, 3 electrons. Okay? If I look at phosphorus, 15 protons, 15 electrons. If I look at oxygen, 8 protons, 8 electrons. I look at uranium, 92 protons, 92 electrons. Stephen, are you with us, my dear? Yes?
I said yes, I'm listening. Sorry,
Okay.
I was just connecting my computer charger.
I see. Okay.
Yeah.
So, and the last one, let's take gold, right? Gold is 79, which means 79 protons, 79 electrons. Okay. So this is information you can take from the periodic table. And right here, this says that they use the color coding in the book. So they label hydrogen as white, carbon as black, nitrogen blue, oxygen red, sodium dark blue. Okay, so let's take a look here. So I was talking about protons and electrons, right? So they equal to their atomic number. What about neutrons? So first of all, neutrons have no charge, right? But also some elements might actually have different number of neutrons, right? Different could be more neutrons, could be less neutrons. The charge doesn't change because neutrons have no charge, but the weight can change because of this. So basically, you know what, let me just write it for you here. You see, this is isotope. So isotope is atom with altered means different number of neutrons. Okay, and the thing is, because a different number of neutrons, because of different number of neutrons, especially if there are extra neutrons, atom becomes less stable. What does it mean less stable? This extra neutron tends to break down and emit smaller particles. Surprisingly, guys, I told you, atoms made of particles, right? But this particle is actually made of subparticles, even smaller ones. So once they start to emit them, this is called radiation. So usually isotopes are radioactive. Some have very strong radioactivity, some have very, very mild, right? But this, for example, shows you carbon, right? So carbon has 6 neutrons, 6 electrons. This is regular carbon. It's called carbon 12. 12 doesn't correspond to atomic number. It just basically says 6 protons and 6 neutrons. But there is a carbon that has extra one extra neutron. There's carbon 14 that has 2 extra neutrons. Okay. So carbon basically breaks down very, very slowly, super slowly. But those that break fast, they used a lot in technology, right? For example, X-rays, CTs, PET scans, they all use radioactive elements because you can trace them, right? You can trace radioactivity. Okay, so what I really want you to know, I want you to know what is isotope. Isotope is atom that has a different number of neutrons. Okay, so this is regular carbon, and these are 2 isotopes of carbon. One has extra 1 neutron, another has extra 2 neutrons. Okay, you see, when they break down, as I said, they release particles that carry a lot of energy, and this can be detected. And this could be used for various purposes in physics, in medical and medicine, in chemistry. And as I said, from all elements, 92 found in nature, 25 present in human body, and the big 4, those that make up the bulk of our cells. One more time: oxygen, carbon, hydrogen, nitrogen. This is pretty much reflects the makeup, but I should say the most common element is still hydrogen, even though it's only 9.5%, but because hydrogen is so tiny, this is the smallest of all chemical elements. In terms of abundance, it's definitely number 1. So this big 4, right? They make 99.9% of your body. Other 4, calcium, sulfur, phosphorus, sodium, potassium, chlorine. And there's also called trace elements that you have less than 0.1%. And trace elements will include iron, for example. It will include copper. What else it can include? It doesn't really matter right now, but remember, big 4, oxygen, carbon, hydrogen, nitrogen. And so you have elements, right? And some of them just the way they are, like I showed you, noble gases. They don't really react with other elements, but most of them actually form bonds, right? And form molecules or compounds, okay? So how do they actually form bonds? And let me explain you something here. I'm gonna go like very, very basic, super basic. So, and ask me questions. If you don't get it, please ask me a question. And as I said, don't really worry about this material, okay? So I told you in atoms, you have protons with positive charge, have neutrons with no charge. And you have electron, okay? So this is atom of hydrogen because hydrogen has 1 proton and 1 electron. If you look, for example, let's say at nitrogen. Nitrogen is number 7, right? So nitrogen in the nucleus has 7 protons, 7 neutrons, right? And it has 7 electrons. Now, electrons, I told you, move around the nucleus and they form a cloud. But even though they move and form a cloud, they have actually, they do have an orbit, right? It's just appearance as a cloud, but they have a path, right? And orbits that they move around their nucleus, they actually called electron shell. Shell is the orbit. Interesting thing that the first shell can take only 2 electrons. Okay, this is for the first shell. Second shell, and we're not going to go further than second shell, can take 8 electrons. So nitrogen is number 7, which means the first shell will take 2, and the second will take only 5, right? Because 2, 3, 4. Okay. So for nitrogen, 2 on the first shell and 5 on the second shell. You follow so far? Now,
Sorry, I have a quick question. So for the quiz, I was not able to access the
yes,
quiz.
I know, guys. I will talk about this. Yes, I know some people were able to take it, some people were not able to take it. I'm sorry. It's like I probably pressed the wrong button, but I'm gonna leave you 30 plus minutes by the end of the class so you can take it. Those who couldn't take it, I will change the settings so you'll be able to take it by the end of the class. Okay? Yes, sorry about that. Okay, so back to shells. You follow, guys? 2 electrons for the first one, 8 for the second. But not all elements, you know, have electrons to complete the outer shell, like nitrogen, right? So nitrogen has 5, so it has 1, 2, 3 spots, right? So nitrogen has 3 spots for electrons. Yep. Now, everything in this world stands for stability. Yes, we want to be stable. Cells want to be stable. They want to maintain stability, and elements want to maintain stability. So stability means for chemical elements, complete outer shell. How can you complete the outer shell? It's a good question. If you, for example, have, let's say, if you look, for example, at lithium, right? So lithium is number 3. So lithium has 3 protons, 3 neutrons, 2 electrons on the first shell, and 1 electron on the outer shell. So for lithium to be stable, the best way is just to get rid of this electron. Just give it away, right? They can do it. For example, for oxygen, and oxygen is number 8, right? So 8 protons, 8 neutrons, and then you have 1, 2 on the first shell, and you have 1, 2, 3, 4, 5, 6, right? But the other one can take 8. So for oxygen, to have it complete, is basically to pick up electrons from another element. So basically what elements do, they either give or pick up. But bottom line, what they do, they share electrons. So by sharing electrons, they form bonds, chemical bonds. By sharing electrons, they form molecules and compounds. Let me show you 2 more things. I hope you will get it. Hydrogen is an element, right? It's a gas, but it tends to make a molecule of hydrogen. Molecule of hydrogen is H2. Okay, so very easy. 1 proton, one neutron, one electron, one proton, sorry, one neutron, another electron. Do you remember how many electrons could be on the first shell, guys? How many electrons? First shell can take 2, second shell can take 8. So first shell, 2 electrons. What hydrogen does is basically shares, 2 hydrogen share 2 electrons, right? They share electrons, they form a molecule. Okay?
And if
That's
you
how they,
combine monoxide, you get water.
yeah, like oxygen, very good example. So let me do this. I'm just gonna write it first,
Sorry.
2, second, 8, right? So for example, oxygen, yeah. So oxygen is 8. 8 protons, 8 neutrons, 2 electrons on the first shell. How many electrons on the second? Guys, tell me. How many electrons on the second?
8.
8.
It can
8.
take 8, but
6.
6. 1, 2, 3, 4, 5, 6. How many more they need? They need
2 more.
2 more, exactly. So they can take it from hydrogen, right? They take 2 electrons from hydrogen, and this is H2O, right? So if I go back to here, right? So what I'm saying, stability, unstable atom, hydrogen, because it has, again, it has only 1 electron on the outer shell. Helium is stable because it has 2, right? Nitrogen is unstable, it has 3 spots. Neon is stable, it has 2 on the first, 8 on the second. That's why they don't, I told you, noble gases, they don't react with other elements because they're stable. Oxygen has 2 spots, right? So if you have on the outer shell 1 or 2, you usually give them away. If you have on the outer shell 6, 7, 5, you tend to pick up from another element. Oxygen tends to pick up while hydrogen tends to give away. Carbon is, we're gonna talk about this, really unique. Carbon is number 6. So it has 2 on the first shell, 1, 2, 3, 4 on the outer. So carbon can pick up 4, right? So because of this ability, right, it tends to bond with many, many other elements. And it tends to bond with oxygen, right? Carbon dioxide, CO2. It tends to bind with hydrogen, with nitrogen. We're going to talk about this in the second part of the class, about very unique properties of carbon. And another thing is ions, okay? So if one element gives away electrons, right? For example, we'll take hydrogen, right? So hydrogen is 1, right? And when hydrogen loses electron, right? So the top charge will be, if you have 1 proton, 1 neutron, you had electron, but it's gone, right? What will be the charge? What will be the charge, guys?
I'm sorry, say it again. I'm sorry.
If hydrogen loses electron, right? So what will be the charge on the hydrogen atom?
Neutral, nothing.
Positive. It has one proton, right?
Oh, okay.
Remember, number of protons and electrons is the same. Let me just. Sorry. Okay. So this is, yeah, so hydrogen gonna have positive charge. So if hydrogen lost electron, let's say another element can pick it up, right? So let's say chlorine. Chlorine picked up electron from hydrogen. So it's gonna have extra electron. So the charge will be negative, okay? Atoms, and I want you to write it down, atoms that either lost, charge will be positive, or gained, charge will be negative, electrons, called ions, okay? So ion is element with, again, either extra number of electrons or missing electrons, right? So if you lose electron, you're gonna have extra positive charge, right? Because minus is gone, so you have plus, right? More plus charges. If you get electron from another one, you're gonna have surplus of electrons, negatively charged particles. So the charge will be negative. Yes, guys, are you with me?
Yes, I'm
yes.
just not getting much of this chemistry.
It's not even, I mean, this is like not even chemistry. Trust me, I know what is chemistry. I know like how tough chemistry can be. This is like nothing really. So again, you can lose electron. First of all, they lose electrons because the electrons move a little, like too fast, right? And as I said, if you have only one or two on the outer shell, they tend to run away from you, right? You lose, you have extra protons, right? Positive charge. One loses, another gains, right? You gain electron, you get a negative charge. That's how it works. And this actually shows you ions, like for example, sodium ion. Sodium has one electron on the second shell, sorry, on the third shell. And this electron tends to wander. Now, if you talk about cells, it's really a lot about charges. You don't have that many molecules that have no charge on them. Usually, the way cells work, the whole organism works, is due to interplay in ions. So ions, I should say, is more common form of existence of chemicals rather than, just molecules without charge. So in this case, right, sodium will have positive charge. Chlorine has negative charge. Positive and negative, they tend to stick to each other, right? So this is actually called ionic bond. Ionic bond, when you have two ions with opposite charges that stick to each other. And as I said, atoms bond together to form molecules. So molecules could be, again, kept by what I showed you, covalent bond. Covalent bond is when they share electrons. They could be held by ionic bonds. And energy. So energy to form bonds, to break bonds, actually matters a lot. And bonds formed or being broken usually happen during chemical reactions. And as you heard about them, right? And so here you see there are different ways how to present molecule structure. This is molecule of methane, CH4. This is CH4. And usually if you have a bond, single bond is just a line, right? So this is called Lewis model. This is carbon with 4 hydrogens. This is called ball and stick model. I'm probably like that's what people do at school. Ball and stick model. And this is called space filling model, but I usually tend to use this one, the Lewis model. So covalent bonds. Covalent bonds, as I told you, when atoms share electrons, exactly as I showed you with hydrogen, right? One spot, another spot. Why? When we get together and share these 2 electrons, right? That's how molecule of hydrogen is formed. Again, this type of bond is called covalent bond. Oxygen shares 2 electrons, okay, each. So in case of, for example, for hydrogen, it's going to be HH, right? It's H2 because they share only 1 pair of electrons. So this is one line. Oxygen shares 2 pairs of electrons. So it's going to be like this. Okay. Nitrogen, for example, shares 3 pairs of electrons. That's going to go for nitrogen. At the same time, you can write it down, O2, N2. Okay. So it could be single covalent bond, double covalent bond, triple covalent bond. Okay? Covalent when they share electrons. Ionic bonds, as I said, oppositely charged ions. Sodium, positive charge, chlorine, chloride, negative charge. This is table salt, right? You see? Pluses and minuses tend to stick to each other.
Wow, that's actually quite interesting.
I think so too. And another interesting type of bonds is called hydrogen bond. And let me explain to you what is hydrogen bond. So for hydrogen bond, I have to explain you about the water. Let me share the white one. Okay, so water, you all know it's H2O, right? Did you learn that water looks like Mickey Mouse? Did you learn about this? So oxygen is 8, right? Hydrogen is 1. This is their number of protons and neutrons. So in oxygen, you have 8 protons, you have 8 neutrons. On the first shell, you have first electrons. On the second shell, you have 6, right? 1, 2, 3, 4, 5, 6. So it has room for 2 electrons that it can take from hydrogen, right? Yeah, guys, you follow so far? So the thing that what happens when hydrogen gives its electron to oxygen, hydrogen stays slightly positive. And oxygen tends to pull electrons that have negative charge to the opposite side. So oxygen becomes slightly negative. Basically, if you look at the water molecule, right, it's going to look something like this. Negative charge here, positive charge here. So like upside down Mickey Mouse, yeah? Having uneven distribution of charges over the molecules make the molecule polar. So water is a polar molecule. What does it mean? It means on one side it has negative charge, on the other side it has positive charge. So it's like a magnet, yeah? If you have a bunch of magnets and you throw them together, what are they gonna do?
They're gonna stick together.
Exactly.
Yeah.
They're gonna stick together. That's the case. So they're gonna stick together, and that's what water molecules do. So they stick together because hydrogen they stick together because hydrogen has positive charge and oxygen has negative charge. So if you
Are
take
these
water,
atoms?
these are molecules.
Oh, okay, so these are not atoms.
No, this is oxygen, this is hydrogen. So hydrogen, hydrogen, oxygen, oxygen, hydrogen, hydrogen, right? So let me just use it. So this type of bond where positively charged hydrogen attracts to atom that has a negative charge on it is called hydrogen bond. Okay, so this is a hydrogen bond, guys. Hydrogen bonds basically keeps water molecules together, but it also keeps a lot of things together as well, as you're gonna see later. So this type of bond, when you have, one more time, slightly positive charge on hydrogen, right? And in case of water, you have slightly negative charge on oxygen, or it can be another molecule that has a negative charge on it, on one side, another polar molecule. It's a fairly strong bond, the hydrogen bond, and it plays huge role, again, in chemistry and biology. Guys, talk to me if there are any questions.
All right, my question is that so the basic gist of your whole lesson is that you're teaching us about how molecules react to each other, how the inner and outer rings of positive and negative charges, and how they form together, covalent ionic bonds, negatives and positive attractions.
Yes, lab, yes, exactly. I'm teaching basics of chemistry, so I'm talking about chemical elements. I'm talking about the properties, what's the structure, their properties, how they make bonds to form molecules, right? How they interact with each other, exactly. So the secret life of chemical elements.
I don't know why I'm not getting this as much as I should, given that I like nuclear fusion.
Okay, guys, do you have any questions? Do you follow me? Do you?
What's the best way to understand all of this when you're studying it?
The best way, I should say the best way is to think about the charges.
The
Just to
charges.
think about this interplay of pluses and minuses. I think this is the easiest way to understand. But let me just show you about the water, so maybe you get more about that. Guys, any questions? Talk to me, please. For how many of you this is absolutely, completely new information?
Well, this isn't new information to me. I'm just being reminded of it. I'm not very. The last time I learned chemistry was in high school, and I failed. And that teacher eventually became my math tutor.
I see. So, guys, you don't talk to me. So let me just continue then. Let's talk about water. So water is H2O, right? And this is another way. Just look. This is the hydrogen bond. So positive hydrogen, slightly negative oxygen. One more time. Sorry, guys. Can you raise your hand or whatever if you do understand why oxygen is slightly negative and hydrogen is slightly positive in water molecule? Raise your hand if you have no problems with that. Or tell me, gonna go over this one more time.
Okay. Why are they called weak bonds and strong bonds?
I'm gonna talk about this, but can you tell me if you want me to go one more time over hydrogen bonds?
Yes, please. Yes.
Okay, thank you. Thank you. That's what I was trying to get from you. Okay, so look one more time. So this is a Mickey Mouse. Let me just this way. One more time. Oxygen is 8, right? So it has 8 protons, 8 neutrons. in the nucleus. Then on the first shell, remember, 2 electrons. On the second shell can be 8, right?
Yes.
But
Yes.
actually, how many on the second shell? In
6.
6, exactly, 2. 1, 2, 3, right? So to fill the second shell, it takes electrons from 2 hydrogens, right? So this is hydrogen, this is hydrogen. So hydrogen gave away electron, and this hydrogen gave away electron. So this is a complete outer shell for, so both happy. Hydrogen is happy, oxygen happy. But what happens when hydrogen gives away electron, it gets slightly positive charge. Oxygen tends to pull these electrons to the other side. So oxygen gets slightly negative charge. So if I draw a magnet, it's gonna be pretty much the same thing. Magnet has plus, magnet has minus, okay? So this molecule is sticky. If I take one water molecule, right? And this is distribution of charges in one water molecule. And I take another water molecule, like magnets, they will tend to stick to each other. Plus will go to minus, right? And minus will go to plus. Because of the stickiness, right? The water goes in drops. Because molecules tend to stick to each other. Because of this, water forms puddles. Water forms lakes. Because of that, water flows. Okay. This type of bond where hydrogen is slightly positive and another molecule, right, has slightly negative side, this type of bond is called hydrogen bond. And you can see hydrogen bond is not a bond within the molecule. Hydrogen bond is the bond between the molecules. Guys, how about this now?
Finally, I think
Yeah.
I get it a
You
bit
got
more.
it? You
I
got
understand.
Yeah.
Yeah, I
Okay.
understand.
Awesome. Awesome. So this gives water unique properties, absolutely unique properties. So what is unique about water? There are many things unique about water. First of all, really unique thing about water is water can exist as vapor, gas, right? I should say it can exist as liquid and can exist as ice, solid, right? There's also reason why like 70% of Earth is covered by water, right? And probably it was even more long time ago. And there's also reason why life probably started in the water because of these unique properties. And if I go back to their PowerPoint presentation, so what we can talk about, you know what I'm gonna do? So I really, again, apologize for today's morning when you were not able to access the quiz. I'm gonna cover only this one. And the second one I will cover on Wednesday because Wednesday pretty much that's gonna be the topic, the molecules of life. So maybe I'll start a little bit today. I want to give you time for the quiz for those who didn't take it. Okay, so don't worry. We're not gonna go beyond this scope today. Okay, so hydrogen bonds make water cohesive. Okay, so again, things can move on the water. Things can float on the water. And let me show you something. One of my favorite videos in this topic about unique properties of water. Okay. Guys, can you turn off the sound, please? Not this one. So where's my Zoom? I'm gonna have to. I found something really cool. I found that I can share sound with you. And I can't do it right now. Okay, let me try it one more time. So I share screen. to YouTube. Okay, share computer sound. So you're going to be able to hear this finally.
Some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, really run on water. It bicycles its hind legs, and the tail becomes a counterweight. We can't know what the snake is thinking. Did it really want to eat the lizard, or did it just want to show?
Isn't it a cool video, guys?
That was awesome.
I think it's awesome.
Yeah, it's very cool.
Yeah,
Uh-huh.
I wish I could
Yes.
walk on water.
Yep. I mean, lizards can run, a bunch of insects can run. And what happens, what you can see, because these molecules stick to each other, right? This is what's called the surface tension. But again, water cohesive. Cohesive means, yes, it sticks. It sticks, and because of that, you know, molecules form like a layer, right? A layer for some creatures strong enough to move on it, right? Again, that's how, did you ever do an experiment when you can have a paper clip floating on water? Anyone knows this one? I knew how to do it. Maybe I'll show you on Wednesday, this one. Okay, and because molecules stick to each other, they can move as a flow. Again, they flow. That's how the water actually goes all the way up in their very tall tree, right? By the sticky. Okay, give me one second. Okay. Yes, so sticky, right? And that's how one molecule can actually pull another one and another one, another one, all the way to the top of the tree. And also another interesting thing about water is high heat capacity. What does it mean, high heat capacity? Heat capacity means it takes a lot of energy actually to break these hydrogen bonds between the molecules, right? Sun can cause evaporation. You heat water on the stove, right? You cause evaporation, but it actually takes a lot. Anyone you probably paid attention that if you, for example, again, you heat water in the pot, right? The pot will heat up much faster than the water itself, yes? Yes, guys?
Yes, correct.
Absolutely. I mean, if you ever try to heat alcohol, my goodness, alcohol, basically gonna start evaporating in no time. If you ever try, for example, acetone, the nail polish remover, no time. But water actually has a very high heat capacity, higher than many other substances, which means, again, you have to apply quite a lot of energy to disrupt these bonds, okay? And what you can see, once you disrupt them, right, new bonds will be formed. And this is also a reason why once the water is, let's say you go to the beach, right, and the air is hot, but the water is still cold, yes. What happens? It actually happens pretty much due to change in temperature during the night and during the day. In the night, temperature goes down. So actually the water kind of gives away the heat to keep the air warm. When the water gives away the heat, the water temperature will go down and the air temperature will go up, right? That's in the morning, the water is cold. I should say in countries where temperature at night doesn't really drop down much, the water temperature will be stable. Like for example, around the equator, right? You don't see much difference in the water temperature during the morning, right? And by the end of the day. But also this high heat capacity doesn't allow the water freeze all the way down in the lakes and the rivers during winter, right? And many organisms like fish can still live on the sheet of ice, right? That's because of the water's heat capacity. It's not easy to warm it up, right? To disrupt the bonds. And it's also not easy to turn it into ice. And another thing here is, do you ever wonder why ice floats on water? It's actually solid. Why doesn't it sink? Did you ever wonder why it happens?
Yes, I always have wondered.
Okay, so now you gonna get the answer. Look, in the frozen water, look, these are the hydrogen bonds, and you see the distance between the molecules is actually bigger than in liquid water, right? So liquid water, actually molecules tend to stick to each other much closer. That's the difference in density. Actually, ice, surprisingly, has less density than the liquid water. Because of this less density, again, it floats. And like, again, because of that, the spaces actually allow oxygen and gas exchange, again, for fish that live in the river or in the lake during the winter under the ice, okay?
So I have a question.
Yes, please.
So if you had like the same, like if you had a cup with like the same, I'm trying to think of the word, like, you know, when you fill it up, what's it called? Not, you know, the same capacity to hold something, I guess I should say. If you filled it one with ice and one with water, would the one with water be heavier then? Even if it was like the same amount?
It's not the heavier, I mean, yeah, actually, yes, increased density, yes. Water will be heavier than ice, you're absolutely right, yes.
Okay.
Ice gonna go to the top. Mm-hmm.
I'm
Okay.
just curious.
No, it's an excellent question, Ramsey. Seriously, it's a good question. Okay, guys, listen. It's right now is 9:50. So let's say 10 minutes. Okay, 10 minutes break. I'm gonna change the setting for the quiz. So from 10 to 10:30, I'm gonna finish this material, right? And from 10:30 to 11, I will give more time for you. You'll be able to take the quiz, those who are not able to, okay? So meanwhile, I'm gonna change the settings for you. So let me post, let's go back to water. So water is something called a universal solvent. I didn't share the screen, so let me share the screen. Water is a universal solvent. What does it mean? When you mix things with a liquid, again, liquid can be water, liquid can be alcohol, liquid can be milk, liquid can be coffee, whatever, right? So you create something called solution. So solution is liquid mixture. For example, when you mix sugar with your tea, you create solution. Solution has two parts. It has solute. Solute is what you mix. And you have solvent. Solvent is what you mix with. So water is a great solvent because you can mix a lot of things with the water. Tell me what you can't mix with the water. What doesn't get mixed with the water? Oil, exactly. Yes. So usually you can divide things into those, you can divide substances into those that get mixed with the water and those that don't get mixed with the water. And let me write down for you something quite important in chemistry and in biology. So substances. Substances can be hydrophilic. What is hydrophilic? Hydro means water, right? Does anybody know what is philic? Loving, okay? It's like water loving. So hydrophilic mix with water. And again, it's majority. Most of the things get mixed with the water. Like sugar, like salt, like sugar, salt, like acetone, like starch, okay, whatever. And hydrophobic. Hydrophobics, they don't mix with water. Hydrophobic means they hate water, right? So philic love water, hydrophobic hate water. And I can give you a hint actually. All hydrophilic, they have a charge. So there is some charge on them. Either negative or positive. Hydrophobic have no charge. No charge. And again, hydrophobic, oil, fat. And there's also actually extra group called amphiphilic. Anybody knows what does it mean, amphi? Amphi, like from word amphibia. Amphibia means what?
Both water and land? I don't know.
Yes, both, right? Amphibians, both. So amphiphilic means they actually interact with both. They interact with hydrophobic and hydrophilic. There are not too many of them, but a very good example of amphiphilic substance is soap. Let me explain to you. If you have grease on your hands, can you wash it with the water?
Yes, but it'd be very hard to take off. That's why you need soap. That's why you need.
Can you wash it off without soap?
No.
No.
Maybe.
No. Even like with a very hot water, you won't be able to wash off grease without soap. So what happens with the soap? The soap molecule at one end interacts with grease. On the other end, the soap molecule interacts with water. So basically what it's like a carrier, right? One end, it picks up grease. On the other end, it picks up water. And here you go, it's gonna wash it away. So this is the amphiphilic substance. But as I said, most of the substances are hydrophilic because most of the substances, they have slight charge, right? And charge actually makes the whole thing much easier to mix with the water. So I go back to PowerPoint and you're gonna see. So what do you see in this picture? You see how salt dissolves with the water. And remember, sodium chloride. Sodium chloride breaks down to sodium ions and chlorine ions. Sodium ions have positive charge. Chlorine ions have negative charge. So what happens? Those with a positive charge will stick to oxygen that has a negative charge on it. Those that have negative charge will stick to hydrogen that has positive charge. Okay? So remember, water molecules has plus and minus. Plus from the water molecule will go to particle with negative charge. Minus on water molecule will go to particle with a positive charge. So basically what happens, the water molecule will break them apart, right? Literally. That's what happens. So that's why water is a solvent, because it will always interact with particles that have charge. Are we good here?
Yeah.
Talk to me.
Yes.
Okay. Okay, and the very last part here, and this is actually a very crucial part, is about acids and bases. So I go to whiteboard. And again, water is H2O or it's HOH, right? So sometimes what happens, this hydrogen kind of runs away and you get a hydrogen ion, right? This is the most common ion, hydrogen ion. And this ion, OH, is basically oxygen plus one hydrogen plus extra electron. This is called hydroxyl ion. You take water, right? And in water, it's balanced. The amount of hydrogen ions and hydroxyl ions are the same, balance, right? So this is water. And whenever it's balanced, we call this solution neutral, right? It's neutral. Now let's say you add to water, let's say you add hydrochloric acid, right? You mix hydrochloric acid with the water. This is hydrochloric acid. And you mix it with H2O. What happens? You're gonna get hydrogen ion, chlorine ion, you get hydrogen ion, and you get hydroxyl ion. So you get a lot of hydrogen ions in the solution. The more hydrogen ions you get in solution, the solution becomes acidic. So in acidic solution, you have a lot of hydrogen ions. I'm gonna draw it one more time. HCl plus H2O, you get hydrogen ions, chlorine ions, you get hydrogen ions, and you get hydroxyl ions. The more hydrogen ions you have, acidic. Now let's say you mix baking soda. This is baking soda, right? Mix with H2O. And you get nitrogen, and you get hydroxyl ion, and you get hydrogen ion, and you get another hydroxyl ion. The less hydrogen ions you have, and more hydroxyl ions you have, this solution is called alkalinic. And another name is base. Why it's important? It's actually quite important because concentration of hydrogen ions can change property of solution greatly. Whenever we talk about acids, right? What do we know about acids? Okay, let me give you an example.
They burn, right?
Yes, yes. Like, what's the most common household acid is that you usually have at home?
Vinegar.
Is it bleach?
Absolutely, vinegar, right? Can you drink vinegar? I won't recommend you, yes.
Not
Vinegar,
purely, but
yes, vinegar is a strong acid. It burns, right? Acids are sour. Another very common acid that you normally get is citric acid. Citric acid is found in lemons, right? Citric acid is found
lemon.
in oranges, in tangerines, right? It gives this sourness. Did I ask you, can you eat lemons, like raw lemons? Did I ask you already? Yeah, so this is
Yeah.
like because of the strong citric acid. Yep. So what acids also do? They corrode metals. Corrode metals means they destroy metals on the long run. That's why acidic rains, I'm sure you heard about acidic rains. They're quite like unfriendly to cars, right? For example. What do we know about bases? So the very common base definitely is baking soda solution, okay? And another basis, like most of the household items you use to clean things, I mean, Drano, you know Drano, the one that declogs their pipes, actually, is also very strong base as well. So while acids taste sour, bases usually taste bitter, like chalky, so quite unpleasant taste, I should say. And if I go back to PowerPoint, so let's take a look. And that's what I was talking about. Hydrogen ion, this is hydroxide or hydroxyl. There are two ways, hydroxyl and hydroxide ion. And this is actually a scale. It's called pH scale to measure concentration of hydrogen ions. It's actually a logarithmic scale, but don't really worry about this. Anyways, scale goes from 0 to 14, okay? 7 in the middle is neutral. There are a bunch of things that are neutral. Like again, the best example is water. But if you take, for example, table salt mixed with water, it's also going to be neutral. Actually, salts are usually neutral, even though they have charge, but they're neutral because they don't have hydrogen and they don't have hydroxyl ion. Again, the lower pH number, the stronger the acid. So acids run from 0 to 7. Again, close to 0, they're very strong. Closer to 7, they are weaker, much weaker. For bases, again, around 7, weak bases, to 14, these are strong bases. Again, in our body, a very strong acid is hydrochloric acid in the stomach. It's a very strong acid. So I guess you all threw up at least once in your life, yeah? Anyone here who never ever threw up?
Yeah,
you never threw up, look.
I know I have thrown up a lot.
Okay, so tell me, how does it feel in your throat?
Corroded.
Yes, it burns because it's a very strong acid. And you need this acid actually in your stomach for two reasons. First, it kills germs that you get with the food. Second, it helps to digest proteins, something we're going to talk about on Wednesday. Okay, so it's a very strong acid. All sodas are acidic. That's why drinking too much soda is not good for your stomach because you already have acidic environment there. You don't really want to add acidity. Again, juices, most of the juices, like tomato juice, when tomato juice is acidic. Coffee without milk is acidic as well, okay? But so it's a weak acid. Have you ever been stung by ants? You know, there's some ants that sting. They release acid, it's called formic acid. It burns, right? It does, yeah. Now, blood. Blood's slightly alkalinic, and actually human body makes a great effort to keep it that way, alkalinic. Baking soda, alkalinic. Ammonia is alkalinic. Bleach, alkalinic. Again, strong. One more time. whatever is close to 7 is weak. Whatever is close to 0 is highly acidic. Whatever is close to 14 is highly alkalinic. This is again summary for you actually, and I can, before I'm gonna talk about buffers, you know what, actually I'm gonna tell about buffers. So buffers are special substances. If you talk about cell, if you talk about blood, they actually regulate pH and keep it stable. So as I said, pH of blood is slightly alkalinic. It's like 7.35. That's the pH of blood. So buffers can actually either remove hydrogen ions. If they remove hydrogen ions, pH gonna go up. If they release hydrogen ions, pH will go down. So these buffers keep, again, blood pH stable by either removing excess of hydrogen ions or giving. So what I want to show you right now, and this is also going to be your assignment, guys, I'm going to explain it to you. The question is, what will happen if you mix acid and base? Does anybody here can tell me what's going to happen if you mix acid and base?
Is it gonna get clumpy? Like
What?
It's gonna get like it's gonna evaporate?
Evaporate? Not exactly.
Would it be reactive? Like would it bubble or something?
Yes. Okay. If you mix acid and base, you get a reaction, chemical reaction, and this reaction is called neutralization. So let me write it for you. So you mix acid and base. Now, the most common reaction of neutralization is, like, didn't you do at school, volcano? Guys, did you ever do volcano at school? So to do volcano, what do you have to do?
Oh, yes, you have to put in a neutral base and some sort of acid and see it erupt or see it react together.
Okay, so what can you take at home to get a volcano?
You need baking soda and some sort of.
Isn't it vinegar you use usually?
Yes, Samuel.
Yeah, I was
Yes.
gonna say vinegar or some kind of
Baking
acid.
soda. Okay, let me just go to YouTube. So volcano baking soda and vinegar. Okay. Okay, let's watch this one.
It's not playing on the screen.
Yes, so basically what happens is you release, this reaction releases a lot of carbon dioxide, which makes all this fizzing, right? And listen to me, guys. That's going to be your assignment.
Professor, I don't think we were seeing anything.
You didn't see it? I shared the screen.
No.
Yeah, there was no video.
Yeah, but the screen just showed like a set volcano.
I'm so sorry. I'm so sorry. I'm going to do it again. I'm going to do it.
That was
Play it again.
loud.
Nah, don't worry, don't worry. I just couldn't see anything. That's why I thought you were frozen.
No.
I thought my Spotify was still on.
No. Okay, why didn't you tell me earlier? Okay. Can you see it now?
Yeah.
So baking soda and vinegar. Add food coloring. Okay, so did you see it now? Okay, so assignment.
No.
Can you see whiteboard? So your assignment, I want you to be creative. I want you to build a volcano. Whatever you want to use, I recommend you take a plastic plate, right? You can take a plastic plate or paper plate. Plastic is better. Take like clay, Play-Doh, whatever. Build a volcano with an opening on top. Okay, so put at the bottom baking soda. Okay. And then take a glass. You can take vinegar. If you have citric acid, I will recommend citric acid. It doesn't smell that bad. So you can just take like crystals of citric acid mixed with the water. You don't have citric acid, take a glass of vinegar, add food coloring. Or you can actually put drops of different food coloring on top of baking soda. That's going to be even cooler, right? Let's say you put like red and green and yellow, like few drops, all with baking soda, right? Then you pour vinegar and you're going to get an eruption. Colorful. You take a video, you send me the video, and you get 5 points. Make it fun. Okay?
Okay.
Yeah? Sounds
Yes.
like a deal.
Yep.
Yes, sounds a deal. So yeah, towards your next quiz, you're gonna get 5 points. But as I said, try to be creative, okay? With a volcano. So it's 10:24. Let me take attendance. I'll share the screen again. I'll take attendance.